In Chapter 4, Notes D, we're going to look at intermolecular forces and how they affect molecule behavior. Remember that intermolecular forces are different than intramolecular forces. An intramolecular force would be like a covalent or an ionic bond, holding a molecule together. Intermolecular forces are between two separate molecules, for example, between two ions, two polar molecules, some specific polar molecules that are very polar, and where we see hydrogen bonding, and then even temporary polarity, as we see in London dispersion forces. These are the four main types of intermolecular attractions. The forces in between molecules are these intermolecular forces, and these are the forces that will hold the molecules very tightly together in a solid or loosely together in a liquid. You may recall that gases are supposed to experience zero intermolecular attraction. An ideal gas would have no intermolecular forces at play. There is, of course, a big difference between an intermolecular attraction and an intramolecular attraction. The intramolecular attraction is what holds a molecule together. Intermolecular forces will hold, for example, two water molecules close together in a hydrogen bond, giving properties such as surface tension. But it's still not stronger than the bond actually holding the molecule together in the first place. So intramolecular forces are much stronger than intermolecular forces. A solid would have the strongest intermolecular attractive forces. It's going to hold those molecules very, very close together, kind of locking them in place with very little free space in between. That tends to create a very regular pattern known as a crystalline structure. Liquids do experience intermolecular attractions. That's what holds the molecules close together. The catch is, those attractive forces in liquids are not as strong as solids. In a liquid, the intermolecular attractions was not enough to prevent the molecules from moving past each other, which is why liquids can be poured, and they would assume the shape of the container that they're in. It is the strength of these intermolecular forces that determines when a substance will be a liquid or when it will be a solid. How closely together will those molecules be held? And so what that means is the strength of the intermolecular forces will actually determine the boiling point and the melting point of the different substances. Of course, these intermolecular forces determine the boiling point as well. In order for a substance to boil, the molecules must overcome all of the attractive forces holding them together in order for the gas or vapor to form. The stronger the attractive forces, the higher the melting point or boiling point in this case. The trend here is that if the molecules are more strongly attracted to each other with stronger intermolecular forces, it will be more difficult to pull them apart. And so you'll have those higher boiling points and melting points with the stronger forces. Of all of the phases, solids are of course the most structured, as the intermolecular forces are the strongest and they are held the most closely together. But even looking at a solid, there are still different degrees of intermolecular forces, the strongest of which would be an ionic solid, then would be the network covalent solid, then metallic solids, and finally, if you only have covalent bonds, then you would have molecular solids. These different types of solids will form different types of structures, usually crystalline type structures as a solid, and they will have different strength in their intermolecular forces. Ionic solids would have the absolute highest melting point, as the ions with complete positive and complete negative charge interact with each other. There's a very strong attraction. When we write the formula for sodium chloride, for example, we are just representing one sodium and one chloride, the ratio. But as we've talked about before, every sodium is surrounded by 6 chlorines, and every chlorine is surrounded by 6 sodiums. So this network is a very strong network or grouping of rotating positive-negative charges. This is going to be very difficult to interrupt these attractions between any two sodium and chlorine atoms. They're going to be very tightly bonded together. Certain elements tend to make more of a network covalent bond. Things like carbon and silicon are really good at doing this. And when they form a network, they create layer upon layer, where not only do you have the interaction between the layer itself, but layer to layer, you would have this interaction. So this, of course, leads to an increase in strength compared to a regular covalent bond. Next one down the list would be a metallic solid. In a metallic bond, electrons are delocalized following the electron C model, and so you see the electrons kind of floating throughout this sheet of silver in this case. This is why metals are so good at conducting electricity. They have all these free-flowing electrons. Here we're going to have the electron and the charge of the nucleus interacting over a greater scheme throughout this entire silver sheet. And so that delocalization tends to lead to a stronger bond than the molecular solid. But it's still not as strong as the actual ions or the networks were. The weakest interactions occur in molecular solids. Remember that molecular means covalent. So these are covalently bonded compounds. And the forces holding these guys together would be the interaction from one dipole to another, which can become stronger in hydrogen bonding when you have very great differences in electronegativity. And then even if you're just dealing with a completely nonpolar molecule, you can also get London dispersion forces at play, which is just from the delocalization of the electrons. For example, a big atom, the electrons are rotating around. At one very temporary moment, you may have more electrons in one spot than the other. So that very partial charge would also help with this interaction, holding molecules together. These three types of intermolecular forces are collectively called van der Waals forces. So that's a new term there. Van der Waals forces refers to one of these three types of intermolecular attractions. Just a quick warning here about something that confuses students sometimes. Sometimes the book will talk about van der Waals forces and dipole-dipole interactions, even though dipole-dipole interactions are a type of van der Waals force. That's the same thing as us talking separately about hydrogen bonding, which is a type of dipole-dipole interaction. So don't let that throw you off. Just because they're specifically highlighting a type of van der Waals force doesn't change the original definition of van der Waals. Let's first look at a general dipole-dipole interaction. Remember that a dipole is simply a polar molecule, or a molecule where one side has a greater electronegativity than the other, and so the electrons would make that side partially negative. When that molecule comes to another molecule, the partially positive side of that molecule would then be attracted to the partially negative side of the other molecule. So this interaction between partial positives and partial negatives is what creates the stronger force, this dipole-dipole interaction. Keep in mind that there are both attractive forces and repulsive forces because there is both a positive side and a negative side of the dipole. Although the negative sides would repel each other, the molecule will twist to make that distance greater, and so then the attractive forces would be greater than the repulsive forces, since your R value is smaller. So then you would have those stronger attractive forces creating the network that holds the dipole-dipole molecules together. Since the interaction is between a partially negative and partially positive side of two separate molecules, the more partially positive or partially negative those sides are, the greater that attraction will be, of course. So if you look at something like water, you're going to see hydrogen bonding. Anytime you have the most electronegative atoms, nitrogen, oxygen, or fluorine, bonded with the least electronegative covalently used atom of hydrogen, you're going to get a very big difference between the partially negative and partially positive side of the molecule. This is the diagram that belongs in your notes. It does a much better job of showing the interaction between two separate molecules. And you can see that the bond is actually between a hydrogen and an oxygen. Sometimes when I draw this, I show it kind of being in between, which is not technically accurate. The hydrogen is actually interacting with the oxygen in these hydrogen bonds. So anytime you have hydrogen interacting with nitrogen, oxygen, or fluorine, we would call that hydrogen bonding, and that is a special, stronger type of dipole-dipole interaction. When you have hydrogen bonding experienced by a large group of molecules, the overall structure will be reordered, and this is now starting to look a lot more like the crystal structures we looked at earlier. This is where the added strength really comes from. The catch is, this added strength takes up more space. Ice floats on water, which is weird because ice is a solid and water is a liquid. Typically, you would think solids would sink in a liquid. So it actually has to do with the density of the water compared to the density of the ice, of course. So at a 4 degree Celsius, you're going to get the maximum density of water, not actually at 0 degrees Celsius once the water has started to experience the stronger intermolecular attractions. It's a good thing that ice floats on top of water too. Could you imagine what would happen to a lake if ice would sink? Ice would continue to form and sink, and before you know it, the entire lake would be frozen. Instead, the ice floats on the top, creating a nice solid structure over the top of the lake so that fishies can stay nice and safe below, and we can ice skate or whatever on top of the lake. Next, let's look at some very similar structures. Methane, CH4, compared to methanol, which would just have an added oxygen for the OH group. So why would methanol be a liquid at room temperature if methane is a gas at room temperature? It all has to do with hydrogen bonding. Methane does not have any oxygens. It is a nonpolar molecule, and you may even recognize that the bonds, being all single bonds, all sigma bonds, won't even have any delocalization in the bonding. With the methanol, you're going to have an interaction between the oxygen in the phenol group and the hydrogen on another molecule. So that hydrogen bonding is going to create a stronger structure and therefore a higher melting point. So at room temperature, the methane has already turned into a gas, or I should have said boiling point. The methane has already turned into a gas and the methanol is still a liquid. Now let's focus on the London dispersion forces, which of course is named after a scientist, not the city. Just like with all intermolecular forces, there should be some kind of attraction between two molecules. But if we look at a symmetrical molecule like hydrogen, H2, there doesn't really seem to be a positive or negative side. There is no difference in electronegativity. That means that one side doesn't typically have more electrons than the other. But if you look at a freeze frame moment in time, you might have more electrons on one side than the other, and that would create an interactive intermolecular force. Let's picture a completely nonpolar diatomic molecule, like hydrogen. The yellow circle here, or oval here, would represent that on average, there is no positive or negative side. So the uniform yellow would represent a uniform electrical charge. While that might be the case overall, if we stop at one specific instant, it's possible that one side has more electrons than the other. So this would give us the partial positive and partial negative that we see in a dipole, but in a nonpolar molecule. We call this an instantaneous dipole, or a temporary dipole. If we looked at a completely different instant, just one instant later, maybe the electrons have moved to the other side of the molecule. So that would reverse or flip so that the negative side is now on the opposite end of the molecule as it was. So if the negative side is constantly flipping back and forth, sloshing around from left to right, we're getting fluctuating dipoles. So overall, we say it's a symmetrical polarity, but these fluctuating dipoles do create intermolecular forces. Believe it or not, even noble gases experience London dispersion forces. They call these monatomic atoms, which literally means one atom atoms, kind of silly. So these would be things like our noble gases, things that do not bond to other atoms. Even that singular atom is going to have fluctuating or sloshing around of their electrons. So you are going to get those instantaneous dipoles that create the London dispersion forces. Let's talk about a hypothetical situation for a minute. Let's say that I have a molecule which has a temporary dipole. So this would maybe be like our hydrogen atom, our hydrogen molecule, where one side of the molecule has a temporary negative charge and the other side has this temporary positive charge. Let's say I have another atom that just so happens at that exact moment to have an even charge distribution, to actually be instantaneously nonpolar. Of course, it's fairly unlikely, but as I said, hypothetically, what would happen? Given that like charges repel and opposite charges attract, that temporarily nonpolar molecule would then become a temporarily polar molecule. We call this an induced dipole. The molecule on the right was induced to become polar due to the interaction with this partially positive charge of the approaching molecule. As the electrons continue to move, you're going to continue to get that interaction. Whereas one molecule approaches, it would then repel a like charge and attract an opposite charge. And so you're going to get this constant rearranging where the partially negative and partially positive sides are constantly trying to find each other. Now picture this interaction over several molecules. No one says it has to be just between two molecules. So if you get big groups of molecules together, you're going to get this synchronized movement where the positives and negatives are constantly trying to find each other. Although the partially positive and partially negative side of the molecule would constantly be in flux, switching back and forth, that sloshing around would always be in synchronization. A common mistake when dealing with London dispersion forces, and to be honest, a mistake I made a lot in college, is to only focus on LDF forces when you're talking about nonpolar molecules or single atoms like noble gases. The truth of the matter is that all molecules will experience London dispersion forces, since all molecules have moving electrons. The catch is it's only really important when it's the only force at play, which is why it is a greater focus with nonpolar molecules and noble gases. So here's a new term, polarizability. It's very closely related to the ability to be delocalized, although delocalized should really be only used with talking about those pi bonds, double and triple bonds, and the ability to share. Polarizability is a much more general term and a more accurate term to describe a molecule's ability to become partially positive and partially negative on the opposite sides. Think of it as the squishiness of the electron. A really good example of this is how the size can affect polarizability. So if an atom is bigger, it has more room for the electrons to move around and would therefore be more polarizable, as the distance could be greater between the partially negative and partially positive sides of the molecules. Since a larger atom will have electrons further and further from the nucleus, they are going to be more and more polarizable. You may also notice that these larger atoms have a larger molar mass or molecular weight, and so one way to kind of sum up this trend is that dispersion forces would increase as molar mass increases. There's a direct relationship between the strength of the attraction and the size of the atom. This trend actually explains the different phases that you're going to see as you go down the halogens. Fluorine and chlorine exist as gases at room temperature. These atoms have the weakest intermolecular attractions, and at room temperature would already be as far apart as they would need to be for a gas with no intermolecular forces. Bromine, on the other hand, is a liquid at room temperature, so it would have a higher vaporization point, so it would not be quite a gas yet at room temperature due to its stronger bonds since it's a larger molecule. Then towards the bottom, your iodine would have the strongest intermolecular attractions. That is a huge molecule with lots of polarizability. So those positives and negatives are going to be much stronger. The intermolecular forces would be much stronger. And so its melting point would be above room temperature. It is not even a liquid at room temperature due to its stronger forces. One thing I really want to highlight is we are talking about these covalent nonpolar molecules with this trend. Keep in mind the melting points were different for the metals because they had metallic bonding as their primary bond. Another thing that can affect the strength of the London dispersion forces is the shape of the molecule. So if you're comparing, for example, two isomers, which have the same types of atoms involved, you're going to look at the surface area. A greater surface area would lead to greater attractions or dispersion forces. Before we compare these two isomers, I want to do a quick recap on the organic chem naming. So pent means 5. So we have 5 carbons in a row. This would be normal pentane. Whereas prop means 3. So I have 3 carbons in a row. Meth would be the 1 carbon each attached at the second carbon in from the propane. So these are our 2 isomers. Notice how they have the exact same formula. 5 carbons and 12 hydrogens. There is much greater surface exposed in the normal pentane than this clumped up 2,2-dimethylpropane. And so that greater surface area means greater polarizability, and so we have more strength for dispersion forces and a higher boiling point. So those are the 2 main factors for the dispersion forces: the size, or kind of related, the molar mass of the substance, and the shape of the substance, looking at the surface area. If those 2 things are equal, then the dispersion forces should be pretty much equal as well. If you have a greater surface area or a larger molecule, you would have more dispersion forces. When you're looking at dipole-dipole interactions, you're looking at the magnitude of attraction. So the more polar or more polarizable the substance is, the stronger the attraction. And keep in mind, those stronger attractions will then affect the melting point and boiling point. A stronger attraction would have a higher melting point or boiling point. As we wrap this up, I want to compare 3 different substances that have a very interesting pattern. If you compare benzene to toluene, or what we would just call methylbenzene here in the middle, the melting point decreases. However, the boiling point increases. And then you see phenol over here with the highest of all. So I'm going to take a deeper look at what's going on. Let's first consider the melting point. So the melting point would be in between the solid and liquid phases, right? So the molecular structure of the solid would be a factor. We have to consider how good it will be at creating a crystal structure. Benzene is a very symmetrical molecule, so that would make it very good at packing. However, toluene, or the methylbenzene over here, is going to not be as good because of this little finger branch sticking off of the benzene. That's going to make it less good at creating a solid crystal structure. Therefore, the melting point of the benzene would be higher because it is better at forming that solid. Boiling point is going to be between liquid and gas. Now we are not worried about the crystal structure. We don't have to consider its ability to pack. So this little finger that kind of got in the way of creating that crystal structure is now going to allow for greater dispersion, which actually is going to increase the strength of those bonds and increase the boiling point of that molecule. The last question we have to answer is, why did phenol have the strongest with both melting and boiling, significantly higher than any of the other melting points or boiling points? And the answer is, of course, hydrogen bonding. We have the oxygen here that will be involved in hydrogen bonds with the other hydrogens as the phenols come together. So that's going to increase the intermolecular forces overall for both the boiling and the melting point. Hydrogen bonding is significantly stronger than the London dispersion forces at play for either the benzene or the toluene. And we'll end with this summary of the different types of forces. Covalent bond just as an example of an intramolecular attraction having the strongest bonds. Then you have your polarity kind of determining the strength of the interactions, with your dipole-dipole interactions being slightly weaker than the hydrogen bonding. And then the weakest would be the dispersion forces, known as the London dispersion forces, or LDF. And that's where the polarizability comes into play, kind of creating those temporary dipoles. So you see the strength is increasing the greater the difference in charge, one of the major patterns in chemistry. That completes Notes D. Next week we'll look at Notes E, and we'll look at some of those network covalent bonds more closely.